Hey guys, what's going on? So in this video, I'm going to talk about the performance programmability trade-off in computer architecture. So if you think about it, whenever a new computer is designed, there's two big concerns, and I'm lumping some things together here, but it's a decent model. The first concern is programmability. So when you're designing a new chip, whether it's a CPU or a GPU or an FPGA, a CGRA, whatever it is, one of the big concerns is programmability. So what range of programs is this architecture going to be able to run? And how difficult is it going to be to write a new program? So, a programmer is going to have a hard time harnessing the power of this architecture, or is it going to be pretty easy? And then the other big concern, of course, is performance, right? So what's the power consumption of this chip? What's the latency of operations? What's the throughput of data coming into and out of the chip? The physical kind of feeds and speeds type of concerns about how fast and how efficiently this chip operates. So we can plot these two things on an axis and look at a few different architectures, and it can be very illustrative. So suppose on this axis we've got the programmability of the chip, and on this axis we've got the performance of the chip. And let's just put CPUs down here, right? So something like the latest Intel processor might be over here, where it's pretty programmable, right? And in fact, it's very programmable. It can run any C or C++ or Java or Python program you want, and the instruction sets in CPUs pretty much represent, some of the best human understanding of how to do general purpose programming. On the other hand, they're not so high on the performance part or on the performance axis, excuse me. And the reason for this is that a CPU is very general purpose. It's a compromise between the demands of a huge number of different kinds of programs that it needs to run. Operating systems, GUI applications, scientific computing codes. There's all kinds of things a CPU is designed to run, and so a CPU is kind of a compromise between the performance demands of a lot of different programs. On the other hand, you might have something like a GPU, and notice that relative to a CPU, GPUs are shifted back on the programmability axis, right? It's not as easy to program a GPU, and actually, depending on how versatile the GPU is, there might be programs that are actually impossible to run on the GPU. And so GPUs are not as programmable, so they're not as far along on the programmability axis, but they're much higher on the performance axis, right? So a GPU has a humongous amount of data parallelism, so for the programs that it can run, and for the programs it's really optimized for, it can be way faster than a CPU, right? A GPU program for, many kinds of matrix operations, or obviously graphics operations, has way better performance than a CPU, because it's optimized for those programs. And if you move back even more to a really extreme case, you have things like ASICs, application-specific integrated circuits, which are microchips that literally are designed to do exactly one thing, or some tiny range of things, like computing Fourier transforms or doing some signal processing operation in a phone. And application-specific integrated circuits are very low on the programmability axis, right? They're very, very close to zero in programmability because they're not very programmable. There's tons of programs they can't run. They're really specialized to do one or a tiny range of things. On the other hand, they're very, very high on performance because they can be completely optimized. All of the area on that chip can just be optimized for that tiny, one application that it's supposed to do really well at. So if you think about the theoretical bounds on these two things, the theoretical bound on performance is given by physical technology limitations. How small are transistors, and how much power do they consume, and how rapidly are they switching? Programmability is a little bit softer, right? So the outer limit of programmability is really determined by human beings' understanding of programming. So basically, how well do computer scientists understand what programming is and how we do it? And that's really what limits how programmable things are. And so within this rectangle, there's a space of possible architectures, right? So if you think about it, you have things like the ASIC and the GPU and the CPU are really on this frontier of possible architectures that could be designed. And on the interior, as I'll talk about in later videos, you have architectures that you wouldn't really want to design. But computer architecture research really is just about exploring this space of possible architectures. And I've placed these guys on a frontier because to illustrate that, for example, if you have a GPU that's really, really optimized, just the most optimized GPU you can imagine, there's no way to make it higher performance without making it less programmable. And similarly, if you have an ASIC that only does one thing and it's super optimized for that one thing, that ASIC might actually have performance that's at the physical technology limits, that we can achieve. And the only way to make it more programmable is to reduce its performance by generalizing it. So there's kind of this frontier at any given time of possible architectures that you might want to design. And computer architecture research is really just about exploring that space and trying to get better performance on important classes of applications. So I think this can be a helpful and interesting way to visualize what people are trying to do in computer architecture research and when they design new kinds of computers. So it's something to keep in mind if you're ever faced with that task, or if you just have to take an architecture course where you think about lots of different design trade-offs. Well, that was all I had, so I'll see you in the next video.